Hi everybody, so in this video we are going to tackle the problem related to eigenvalue problems and how these can be solved with the methods available in perturbation techniques. And so we are going to consider a discrete form of an eigenvalue problem. An eigenvalue problem is written in the following way. So it's a very simple term. We have a linear operator here, which is discrete, so in the form of a matrix times a vector, plus a small perturbation here. So as usual, we assume that epsilon is a small number, and this is equal to an eigenvalue lambda multiplied by the same vector. This is an eigenvalue, and this is an eigenvector x. So we do recognize, of course, that in the unperturbed problem, ax is equal to lambda times x is indeed something that takes the form of a standard or usual eigenvalue problem, which is written in this case. All right, and so in the very generic problem that we consider here, we assume that this eigenvalue problem is perturbed by a small nonlinear term. This term can be nonlinear. You will see that at no extra cost, we can tackle the nonlinearity of B. And what we are interested in is how the eigenvalues and eigenvectors of this problem are changed due to adding this term. The derivation here is taken from Hinch's book, which is quite well detailed on this topic. And so if you want to have more information, probably it would be good also to have a look at that reference. All right, so I'll try to keep the same notations as those he used in the book so that we can also easily switch from the book to the video if required. So in the unperturbed case, we assume then that the problem is, of course, solvable, and we can solve eigenvalue problems. To start with, there's a hypothesis here, which is asymmetric. If it was not the case, then we'll discuss a little bit later what happens. And let's assume so we are able to solve the unperturbed problem, in which case lambda is equal to a certain value a, and x, the eigenvector, is equal to E, an eigenvector. And so if there are many eigenvalues and many eigenvectors, what we should do now is to consider them one at a time. All right, so we consider eigenvalues one at a time. Okay, meaning that if several of them are actually perturbed by the additive perturbation, we need to repeat this operation several times. But you will see that the derivation is quite generic, so this is only at the end that we'll have to repeat. So is it a regular or a singular problem? I would just say that the problem here can be cast into the family of regular problems, because if you just look at the unperturbed problem, this is still an eigenvalue problem, so we haven't changed the nature of the problem. And so it is quite natural here to seek the solution in terms of expansions, like the eigenvector should be expanded like this, and the eigenvalue, lambda, can be expanded with another regular expansion. So this is quite specific here, because I think over the course of what we studied together, this is the first time that we have to have two sequences, one for the eigenvector, one for the eigenvalue. Then what we do, of course, we could notice that x0, and this is expected, is equal to E, the eigenvector that we are interested in, and lambda 0 is equal to A. That will come naturally soon anyway. So what we need to do now is to substitute this in the governing equation. And if we substitute this, we're going to have A times x, which is x0 plus epsilon x1, epsilon square x2 and so on, plus epsilon b, which should be evaluated. This is a nonlinear vector valued function which needs to be evaluated at x, like this. And all of that is equal to lambda. So this is lambda 0, epsilon lambda 1, epsilon square lambda 2, plus additional terms. And we need, again, to multiply this by x0 plus epsilon x1, epsilon square x2, and so on. And what we have dropped for sure are things of order epsilon to the third. We could probably rewrite this and use a series expansion of B. So we will assume that B is sufficiently regular in the neighborhood of x0 so that this can be actually written B times x0 plus epsilon times a Jacobian of B evaluated at x0 plus higher order terms. All right, like this. And this is clearly how we're going to get rid of the nonlinearity of the problem. Okay, so at leading order, I think we can, I'm pretty sure we can collect the terms quite easily. We have a leading term over here. The next term is in epsilon, so we don't have any leading. Up, so what we're going to have is a times x0 is equal to lambda 0 x0. This is the unperturbed, in fact. All right, as expected, which means that as we were hoping, x0 is equal to e, the eigenvector that we want to consider, and lambda 0 is a, the eigenvalue that we want to consider. Okay, keep in mind that e and a, they form pairs. All right, so they go together. Don't ever mix an eigenvector with a wrong eigenvalue. At the next order, which is order epsilon, what do we have? We have this term, epsilon x1 over here. We'll have the leading term over here, b of x0 multiplied by epsilon. And on the right, there will be crossed terms like those. All right, so let's write this out. There will be a times x1 plus b x0 is equal to lambda 0 x1 plus lambda 1 x0. All right, so probably we can rewrite that equation and keep x1 on the left. So if we keep x1 on the left, you see we have something like what we had before. I can also rewrite this. The equation we should have solved earlier was that one. So I just copy this again. So we can do the same here. A minus lambda 0 I multiplied by x1 is equal to lambda 1 x0 minus b of x0. All right, and so this is a problem. Well, a problem, maybe not a problem, because it's the specific of a eigenvalue problem here. What do we have in that equation? Okay, the equation we have right here, we have a few things that are unknown. We have an eigenvector that is unknown, and we have an eigenvalue that is unknown. So it means that if the system here, which is a discrete system, is a set of n equations, we have n unknowns contained in this vector, plus one unknown over here. So we have n plus one unknown. All right, and that's a specific, of course, of an eigenvalue problem. You have one more unknown than the number of equations you have. And usually this is solved by writing that the some norm of the eigenvector is equal to 1 or is chosen, or one of the component of the eigenvector is chosen. So you add an extra equation in order to make this problem solvable. By the way, it was exactly the same at leading order, all right? So this is a standard eigenvalue problem. And again, you see this is a set of n equations, and we have n unknowns in x0 plus 1 unknown in lambda. All right, but still we can solve that problem. And how do you solve this problem typically? Well, you would start by just writing that the determinant of a minus lambda 0 I is equal to 0. So then you determine lambda 0, and once this is done, you reconsider the original set of equations and you then determine x0. All right, so the sequence is first you compute lambda 0, which is equal to lowercase a, and then you compute x0. So let's try to see if we can do the same here. We would need to find a way to get the expression for lambda 1. The problem now here is that what we have to solve at the following order over here is not something that has the homogeneous form of a standard eigenvalue problem. So the right-hand side is not equal to 0. And so we can't really use the same techniques as those we used before, because simply there's a right-hand side. So it doesn't mean that the determinant of this matrix, of course, is equal to 0. By the way, anyway, this is something we already have exploited before. All right, but because this matrix here is a singular matrix, and it has a right eigenvector x0, it means that this set of equation is something that is really, really specific. It means, in fact, that the right-hand side can't have any component aligned with the eigenvector. Otherwise, it would provide an answer that is non-bounded. All right, and a very simple way to prove this is to multiply this equation on the left by x0 transposed. All right, and so if we do this, we have a projection of the equation on the unperturbed eigenvector, so that we have a minus lambda 0 I times x1 is equal to lambda 1 x0 transposed multiplied by x0 minus x0 transposed times b of x0. All right. And this here is actually nothing but a transposed of a0i x0 transposed, right? And this is equal to 0 because of the leading. Or I'm just translating that x0 is an eigenvector. And so I'm just projecting the set of equation, the second set of equation along that eigenvector. And what I'm going to say is that the right-hand side has no component along x0. All right? And this is because of the leading. I mean, because of the definition of x0. All right? We can just open a small parenthesis here and say that if A was not symmetric, you see that we could write this here, the transpose of A is equal to A because A is symmetric. If A was not symmetric, then there's an extra step to do, which is that at the same time as you compute x0 at the leading, so if A is not symmetric, when you solve the leading, what you need to do is to solve also the companion problem. All right, solve also the companion problem, which is very similar, which just consists in computing the left eigenvector. All right, so x0 is the right eigenvector, and y0 is the left eigenvector. Okay, that's something that is probably quite unusual for most of you, but there's no big hidden difficulty, of course, because if you want to solve this equation, just transpose it and use the tools you're used to use. All right, so if you transpose this is y0 transpose over there, and if you use standard tools, you see that you can recast the problem over here. So y0 is the left eigenvector of A, which is actually nothing but the right, or the usual, if you want, eigenvector of A transposed. All right, and so instead of projecting here on x0, because you see what we would like to have is something on the left that just cancels this out, we would project on y0 transposed, all right, on y0, so just multiply by y0 transposed. All right, this closes the small parenthesis, remark is over. We'll practice this over some exercises, all right? Let's keep going and see what we need to do with what we have. So because I'm starting again then from that equation, we see that we have projected the governing equation at the second order. We have projected that equation on x0 in this case. So we have 0 on the left-hand side. And so we just remain with the right-hand side being equal to 0. And so it means that lambda 1 multiplied by x0 transpose x0, which is the squared norm of x0, is equal to x0 transpose b of x0. Or, in other words, we can also write that lambda 1 is equal to x0 transposed times b divided by the norm, the square norm of x0. So if you're more used to other notations, you could write something like this. I can shorten a little bit the numerator and put it like this. Okay, once this is done, and again, I would say this is the standard approach, right? First, we compute lambda 1, and then once we have lambda 1, we need to compute the corresponding eigenvector, or in this case, the correction to the eigenvector. So we return to the original equation before having projected on x0, right? Because we need a set of equations now, and we don't need a scalar equation. All right, so of course you notice that this is now a scalar equation, which could provide us the scalar unknown lambda 1. So we return to the original equation, and now we know n1, we can replace it in the problem. So we have a minus lambda 0 I multiplied by x1 is equal to lambda 1, which is now known, x0 transposed b, over x0 transposed x0 minus b. Sorry, x transposed b. No, sorry, minus b. All right. And what is this? Well, this is in fact minus b minus x0 transposed b over x0 transposed x0. And you see here that you subtract from b, you subtract from vector b its projection along x0, right? Because the second term in the parenthesis here is a projection of b on x0. And so what remains is just a perpendicular component of b after having subtracted x0. So this is the component of b which is perpendicular to, orthogonal to the eigenvector. And this corresponds, of course, to what I was saying before. What I was saying before is that because the matrix on the left-hand side here is a singular matrix, we can't really have any component along the corresponding eigenvector on the right. All right, and so what we can then just write is, okay, now we can solve the problem as usual, I would say. Exactly as what you did at the leading order. Probably a little bit of exercises will make it more clear. And then if you solve this, let me just write it in probably a strange way, because matrix, the matrix multiplying on the left is a singular matrix, but still we can solve the problem. And let me just write A minus lambda 0 I inverted, okay, like using a pseudo inverse because the matrix is singular, multiplied by the orthogonal component of B to x0. And because the matrix on the left is singular, actually we can add any arbitrary component along x0, and that would still satisfy the governing equation, right? Because you notice here that if you add any number k times x0 to x1, you see that this would cancel out because of the product, right? And so it means that there's no way, because the matrix on the left here is singular, there is no way we can determine the component which is aligned with the corresponding eigenvector. All right, and so k is just here any arbitrary constant. All right, and you may want to choose that constant in such a way to normalize the eigenvectors up to something desired, okay, as you wish to do, or as probably you used to do. Okay, so we have two important things here, which are going to come every time you have perturbed eigenvalue problems. So first you compute the perturbation to the eigenvalue, and once this is done, you can compute the perturbation to the eigenvector. All right, it is really seldom that at the end of the day you write the solution in this form with a pseudo inverse, because, well, that's quite unusual. But at least this is, just by solving the problem, you can get an explicit expression for x1, and this is what you're going to use. All right, I suggest you start with exercises to practice this topic. Exercises related to eigenvalues are collected in series of videos E. All right, so please enjoy and go ahead.